Okay, so thanks everyone for joining in to this. I think this is our third talk of the year. It's really a pleasure to have Claudio Mezzetti with us. He's at the University of Queensland since I think 6 years ago or something like that. And he was previously in Melbourne and then previous to that Warwick and UNC. Claudio, take it away. The floor is yours.
Okay, thank you, Jesse. So let's follow the rule that I don't have to look at somebody raising their hands in the chat, but just unmute yourself and ask the question if you want to. So this is a paper with three co-authors. So Wei is actually a PhD student who's going to be in the market, a student of Tristan Tomalahek, and he very much contributed to the paper by solving the three rider problems that is very severe when there are at least three co-authors on a paper. All right, so the question. So we study a repeated principal agent problem where the sole instrument of information or the principal has is information. So the principal will try and provide incentives for sort of good behavior by the agent through providing information. So the interaction is repeated. So the principal goal is to maximize the discounting number of times that the agent chooses a particular action, which we interpret, as sort of undertaking a project for the principal. There's a crucial assumption, and so important, but crucial to some extent, is that the principal is able to commit to a long-term contract. I'll tell you what the long-term contract does shortly. So the question is, what does an optimal contract look like? Is the principal going to disclose information right away, along the way, the beginning, at the end, and what is what does the agent do along the way? So let's make it clear. The paper is on the technical side of things, and so I think it's sort of fair to say that there is the important contribution, or at least to some extent, the most novel of the contribution is a technical contribution. That is to say, so we set up the problem as a dynamic contracting model. So the standard approach in dynamic contracting model is to use the agent's promise utility or continuation utility as a state variable. So the problem has promise keeping constraint and incentive constraint. So our model is basically a dynamic persuasion model, and so we need to incorporate on top of the promise keeping constraint, the additional constraint that the belief process has to evolve. Belief process, you should understand it as what the agent believes about the state of the world as a result of the information disclosure that the principal makes along the way. So the additional constraint is that this, the belief, are going to follow, a martingale process, right? So there is, the literature calls it Bayesian feasibility or Bayesian plausibility, and so to the best of our knowledge, we have this paper is the first that manages to sort of characterize an optimal contract by simultaneously solving for the evolution of the agent's beliefs and the promise utility. So that is one of the contribution, the technical contribution of the paper. So now, how about the general properties of our optimal policy? So let me spell out So that just as a way of introduction without the general property. So, in the model, there is, the agent, there is an optimal action, there's a favorite action for the principal. So the optimal policy is such that the agent is induced to repeatedly choosing, the principal favorite action and updating, his belief as a result of information disclosures, until, the agent either perfectly learns the state or choosing the principal's favorite action becomes the optimal thing to do. If the agent sort of learns the state, is going to learn it in infinite time. Second point, so which sort of differentiates our paper, from other paper on sort of dynamic persuasion. Along the path at which the agent chooses sort of the principal's favorite actions, the agent's belief move in the direction of the state at which incentivizing the agent is relatively less costly to the principal. So basically, intuitively, what the optimal contract is going to do is going to exploit the fact that there is an asymmetry in opportunity cost of undertaking the principal actions in different states. And so the principal moves, it's going to try and move the beliefs sort of in the direction where incentivizing the agent is easier. So that's general property number 2. So so now in many instances, the optimal policy will not disclose information in the first period. Instead, the optimal policy is going to have the feature of do my preferred actions, says the principal, I'll reward you in the future with some information. Having said that, there are going to be some instances where where persuasion is going to be needed. So for instance, the setting could be one in which even if I promise you that I'm going to tell you the truth about the state, I'm going to design an experiment that tells you the truth about the state tomorrow, that might not be enough to induce you to want to undertake my favorite action today. If that is the case, then I'm going to have to give you some information right away. So in that case, sort of, I'll need you to persuade you right away, as opposed to with the promise of information in the future to do what I want you to do. So that's property, sort of, vaguely property 3. This comes, from sort of the observation that I'm inducing you to undertake you the agent, me the principal. I'm inducing you to undertake my favorite action by promising you that I will reveal information in the future. So that sort of the consequence of that is that when you do that, undertaking my favorite action is not statically optimal for you. So this is different from what would happen, for example, in a static version of the persuasion model by Kamenika and Gengska. Okay, so there is there is this element of using future information disclosures as rewards. So now for those for those of you that sort of are familiar with this literature, let me sort of say a few things that sort of spell out how we differ. So first of all, as I said, the technical contribution sets us apart. Other models of dynamic persuasion I've used simplifying features of the model to sort of make the analysis sort of not requiring keeping track of the evolutions of belief and promise utility in time. So the most closely related paper that deal with with dynamic persuasion in over time are these three. The first one, two of them are basically quitting games in which the agent can undertake work for the principal or quit, and the principal wants the agent to continue working. So there are only two. There are only two actions. So for example, in Ellie and Zidalski, the game is a quitting game, and whenever the setup is like ours, information in their paper comes in lumps, so it's disclosed either at the beginning or at a later period. While in our models, we shall see information is disclosed gradually over time. So that's a difference. Orlov is also a quitting game. In the optimal policy, in Orlov is to fully reveal the state with delay. So this feature that you use information to reward is there, but the optimal policy there, is of the sort: do this for me. Later on, for a certain number of periods, later on, I will tell you what the truth is to reward you. So this policy that is optimal in Orlov is not optimal in our paper. The paper by Ball, is a little different. It's a continuous time model, and also the state changes over time. In our model, we have a persistent states, and so that's a difference. And the optimal disclosure policy is also different. There are a bunch of other papers in which agent takes action repeatedly, but either the agent is myopic or the principal cannot commit. So bottom line, there are a bunch of sort of differences, and you can judge it by yourself. How important they might be, but that's that. So I'm gonna sort of fly through my slides, and you stop me if you have questions. Okay. So let's now start introducing the model. Then I go back to the intuition, I go to the model, etc. So the model is this. So there's a principal and agent. They interact over an infinite number of periods, and there is a payoff. So there is a payoff relevant state, and it takes two values, so omega-1 and omega 0, and is unobservable to the agent. And there is a prior, there's a prior probability about the state being either omega-1 and omega 0. So it's big, sort of clear. We are going to have to keep track of the evolution of this belief, over time as the agent makes disclosure. The fact that there are two states make the belief a single number. It allows us to have a model that we can solve, right? So more than two states, it's something we would like to solve, but we haven't yet. So actions. So at each period t, the signal, the principal send the signal. Really, the principal is committed to send signals that are functions of the history of stuff. The agent observes the signals and then takes an action. The set of signal and action are finite, so the cardinality of the set of signal is enough so that we don't have restrictions. So basically, it's enough that there are as many signals as there are actions, because after all that the signal has to do is essentially tell the agent, do this action, and these are the beliefs that you should have, and this is the promised utility I'll give you in the future. So it's enough that the cardinality of S is the same as the cardinality of the set of actions A. Okay, here's an important restrictions again. So there exists an action A, we are going to call A star, which is what the principal wants the agent to do. So what the principal wants the agent to do is independent of the state, but the payoff that the principal gets from that action can be different in different states. But it has to be positive, and we can normalize, on the other hand, the payoff from we normalize the payoff of any other action that the agent might take, the payoff to the principal from any other action, and the agent might take as being 0. So basically, the principal wants a star, might get a different payoff whether the state is omega 0 or omega 1. Any other action gives 0 payoff. So the agent payoff, on the other hand, can depend in a general way on actions and states. There is a common discount factor, delta. Okay, strategies. Okay, so this is a piece of notation which you don't really necessarily have to sort of memorize, but the idea is a behavioral strategy for the principal. Yes.
Can I ask a question?
Yeah.
Go back one slide.
Yeah.
So why do you need the payoffs? So why do you need A star to be? Why do you need the payoffs of A star for the principal to be different in both periods, or is not relevant at all, and only matters that you have one
different in the two states? You mean?
Yes, in the states. I mean, yes.
I don't need it.
You don't need it. Okay.
It's just that I don't need it. You'll see what I need, but I don't need them to be different. It's just it's just a free extra generality.
Okay, so all you need is an action A star that is the best for the principal regardless of the state.
Yes.
Yeah, okay, cool, thanks.
So behavioral strategy for the principal. So the principal is going to choose a distribution of a signal. So it's going to say today, the strategy is going to say today, the signals that the agents get are signal 1 with probability so, signal 2 with probability so, and so on. And that can be a function of all past history. And what is past history? Past history are the signals that were sent in the past and the actions that the agent took in the past. So when we write the behavioral strategy of the principal in this way, the implicit assumption there is that the action that the principal takes are observable. The principal observes those actions. So the principal could then say, okay, you know what? You didn't do what you were supposed to do. I can see that. So from now on, you're not going to get any information. Right? So that's that. And a behavioral strategy of the agent, basically what the agent does, chooses what action to take. Mixing is allowed. What action to take, again, as a function of all the history of what the agent has done and what the signals have been. So that's the setting. So what's the problem? So the problem is, we can write down we can write down the principal expected discounted payoff, bold B, the agent's expected discounted payoff, which is bold U. And so the problem is to characterize, the maximal payoff the principal achieves if he commits to a strategy thou. So the strategy of revelation as function of past history. The principal can commit it, at the very beginning. The constraint is also that the strategy that in computing is sort of this payoff and the actions taken, etc. The agent choosing strategy sigma that maximizes her expected payoff. Okay, so that's so you can set it up as the principal chooses his own strategy and the strategy of the agent, subject to the fact that the strategy of the state of the agent is got to be optimal. So that's sort of standard, really, in this kind of problems. So now, let's go back to being a little informal for a sec. So let's stress a few things that are important. The state is fully persistent. So there's no change in the state. The principal observes the action of the agent. The only instrument is information. And the principal is choosing the contract prior to learning the state, or the principal does not know the state, but can sort of set up with this information structure that depends on what the state is, right? So the information structure, what signal you send might depend on what the state is, but the principal does not know the state when the contract is set. And again, principal commits to this contract, which specify information to be disclosed at each history or realized signals and actions, nothing else. We sort of don't allow for monetary payments. In fact, perhaps it would be interesting to see what would happen if you did that, but sort of that is something maybe one could do later. Okay, so let me have an example. Yeah, so that things maybe are a little bit less abstract. So okay, so in this matrix you see that there are two states, omega 0 and omega 1. There are three possible actions, A0, A1, and A star. The first entry in a cell is the payoff of the principal. So the principal gets 0 if the action is either A0 or A1, and get 1 if the action is A star. So you see in this case, we take the action to the payoff when action is A star to be 1. Now let's, what about the agent? Well, the agent sort of wants to match the action to the state. It gets a payoff of 1 if it matches A0 with omega 0, a payoff of 2 if it matches A1 to omega 1, otherwise it gets 0. Interesting, there is an asymmetry here, right? So doing what the principal wants, as opposed to doing what would be optimal and the complete information, is more costly to the when the state is omega 1. So the principal has an incentive to try to sort of disclose information, so as to move the incentives, to disclose information towards belief that puts probability on omega 0, so as to make incentivizing the agent easier. All right, so that's what this asymmetry is going to do for us. And so now let's do some quick calculations on the assumption that the discount factor is one half, and the probability that the state is omega 1 is 1/3. So we do some quick calculations about some policies that you might, are going to be certainly familiar to Anton. You could say, I'm not going to tell you anything. That could be the policy of the principal. In this case, A star is strictly dominated. So if you're not going to say anything, never give any information, the principal's payoff is 0. Okay, so you could say, okay, do A star for a bunch of periods, and then I'll tell you what the true state is. Okay, you do a little computation, and you sort of sort out that the maximum number of periods that you can get the agent to do A star is 2. You do a computation of the payoff. You get 1 in the first period, one in the second period discounted by 1/2. You multiply that by 1 minus delta. The principal payoff is 3/4. Okay, so that is better. Here's another policy that does even better. You could reward the agent with full information disclosure with some probability. So you say, I'll tell you the truth with probability 3/4 in every period. Okay, so this policy, this policy does better and gives it gives the principal a payoff of 4/5. So this policy does better than the policy of rewarding at the end with full information disclosure just because of an integer problem. Really, I mean, if you were in sort of continuous time, then the two policies would be equivalent. But okay, in this setting, it does better. So are these policies optimal here? The answer is no. The optimal disclosure policy, does better. It does, rather than 0.8, it does a payoff of 0.83. And the idea is that, as we shall see, what the optimal policy is going to do is going to sort of move sort of beliefs towards omega 0, exploit the asymmetries in the payoff. Information is disclosed sort of slowly over time. So so the rest of the talk is going to try and tell you how we get to to sort of figure out what the optimal policy is in this example and in general, really, or in general in the model that we have laid out. Okay, so we need a little bit of additional notation is going to be used, and I'm sorry. So we're going to call the agent beliefs as P. So just forget about the dependence on the states. P is the probability that the state is omega 1. Okay, we are going to use U of AP as the expected payoff of choosing action A when the agent's belief are P. Right? So that's sort of not too hard to memorize notation. So the utility of the agent as a function action and the belief expected utility. Okay, so now what is MP? Well, when you have belief P, if you could choose the action that maximizes your static payoff. And it's an option that you're always going to have. So this is an important reference point. So you can't, in particular, the principal is not going to be able to push the agent below this reference utility because the agent could say, I'll do my static action. And so we call that MP. Right? So MP, is a piecewise linear convex function. It's the reason why it's piecewise linear is because there are a finite number of actions for different belief, different actions could be optimal, and so that's that. So capital MP, on the other hand, is the expected payoff if you learn the state prior to choosing an action. So, in the example, if you tell me that the state is omega 0, I take action A0. If you tell me that the state is omega 1, I took action A1. I get payoffs 1 in one case, 2 in the other. What's the belief? What the belief is P, so I can compute the expected utility of that. That is MP, right? So MP is the expected payoff if the agent learns the the state prior to choosing an action. Now, VAP is the principal's payoff. When the agent chooses A and the principal's belief is P. So in the example, this is a bit of this notation is a little redundant because you know, the payoff is either 0 or 1, depending on what the action is. But but if the payoff for A star were different, then the notation wouldn't be redundant. All right, so that's the notation. Okay, so I said from the very beginning that, you know, part of the contribution is technical. So how are we gonna tackle this? We're gonna sort of have a recursive formulation of the problem with two state variables. So the agent's promise utility, which we're gonna call W, and the agent's belief, which we're gonna call P. And so a policy of the principal is gonna be a probability lambda s that the realized signal is S. So as I said at the beginning, you're only going to need as many signals as actions. So, you know, lambda S, really, we'll call it the probability that the signal is S. You know, you could think about the probability that the suggested, you know, the recommended action is going to be a S, but let's stick to the plot. So a probability lambda S that the realized signal is S, and then you choose the posterior beliefs when the signal is S. So these are the posterior belief of the agent, right, which are sort of, you know, be set up as if it's something that the principal chooses. So the principal chooses the probability of the signal, the posterior belief that the agent has to have when the signal is S, the promised future utility that the agent is going to get when the signal is X, and the action that the agent has got to take today when the signal is X. So the policy spits out an S, and this S, you know, with some probability, and also given this S, so tells the agent, this is your belief, this is your future utility, this is what you should do today. Now, so we're gonna basically sort of solve the, you know, look at, you know, sort of in classical way, we're gonna look at the value function, you know, value function of the principal. We're gonna try and sort of, you know, obtain it as sort of at the, you know, fixed point of an operator. So the value function of the principal will be a function of the beliefs of the agent and the promise utility, the two state variables, right? So this is, you can think about, you know, it's going to be the value function or the continuation utility of the principal when, you know, when the promise utility of the agent is W and the beliefs are P. Where does it live? Well, beliefs P can be into 0, 1. What about the promise? What about the promise utility of the agent? Well, the promise utility of the agent has got to live in lower MP and capital MP. Lower MP is what the agent is going to get by always doing the static action. You can't promise less than that. And MP is what the agent would do, you know, would expect to get if you promise him to tell him the truth about the state tomorrow. There is no point on promising anything more than that. So that is the domain of our value function. And so basically, so the value function, you know, max, you know, can be obtained. Oh, I don't know if you see, do you see my pictures in? Okay, let's get rid of that. So the value function, you know, can be obtained, you know, in sort of standard function as a fixed point of an operator. So here, what do we have? Here we have that you know, it has to be the case that the choices of probability of each signals, beliefs, promise utility, and action at current period of the agent maximizes the agent expected payoff. So, you know, the lambda S is the probability of getting a signal S. If you get the signal X, the action suggested is AS, the beliefs are PS. So this is the utility of the principal from current action, which we multiplies by 1 minus delta, and V is, you know, the future, you know, future utility of the principal. which has weight delta. So the value function is going to be a fixed point of this operator. This operator embodies the maximization, the choice of the policy that by maximizing of the principal, and also embodies the 4 constraints that the principal must satisfy if you want sort of to choose probabilities of signals, beliefs, and utility of the promise. So if you want to choose probability of signals, beliefs of the agent, promise, utility, and action in a way that respects all the relevant incentives. So there are 4 of them. I'm going to discuss each one of them except the last one. The last one says that the probability over the signal has got to be a probability. So the probability over each signals have got to adapt to 1. So then there are three other constraints, and what are they? Well, the first constraint is an incentive constraint, right? So the agent the agent must get at least a static best reply payoff MP. You get the signal S. If you undertake the action AS and you have the belief PS, UAS PS is what you get today, and then you're promised to get WS tomorrow. That has got to be at least as good as sort of given your belief PS, you do the optimal static thing. So that's the first thing. Constraint is an incentive constraint. The second, the second constraint is a promise keeping constraint. So currently your promise utility is W. The policy sends a bunch of signals, so we can compute what your expected utility is. It will depend on the promise utility. Your expected utility over all signal has got to be at least as much as the utility that you were promised yesterday. So the promise of omega, which was made yesterday, must be honored today, or any promise that you make, any promise omega s that you make today must be honored in the future by the contract. The third constraint is the Bayesian feasibility or beliefs are got to be a martingale. If current, it has to be the case that the splitting, so of beliefs. So you start with some beliefs and then you have different beliefs. Well, the new beliefs have got to be averaging out to the beliefs that you're starting with, right? So that's sort of martingale property or sort of Bayesian plausibility. So in a way, dealing with this constraint together with the promise keeping constraint and the incentive constraint is sort of something that is sort of novel, to our paper, where we think we contribute on the technical side.
Claudio, quick question. Yeah. So why is the promise keeping constraint written with inequality rather than with equality?
It turns out that sometimes you're gonna have to give rents to the agent.
But so I saw that the promise keeping is just sort of like accounting. So this W should incorporate these rents.
Yeah. Let me get back to that when I okay, so let me get back to that when I give you the optimal policy, okay? Is that okay?
Yes.
Okay. Okay, so this sort of let me not sure I care too much about this, but you know, the value function is concave in both arguments and decreasing in W. In fact, the necessity to guarantee that the value function is concave, you know, shapes our optimal policy. So the way to understand this, you know, the more information the principal discloses, the harder it is to reward the agent in the future. And decreasing in W, you know, the more utility the principal promises to the agent, the harder it is to incentivize the agent to play A star. Okay. So let me now spell out some additional general properties that apply, that are going to hold in the solution to our problem. So the principal front loads information disclosure so that A star is always played early on. And as soon as an action other than A star is played, you know, the principal stops incentivizing the agent to play a star, and its continuation value is 0. When the principal recommends a star, you know, the promise continuation payoff does not leave rents to the agent. So the agent is indifferent between obeyed or recommendation or deviating. But when initial beliefs are extreme, we'll see what that means later, the optimal policy must give rents to the agent. In the first period, really, that's what happened. But okay, so here is the assumption that we're going to make, is an assumption that holds in the example that I gave you. The assumption is that, so the assumption, if this inequality is written, if this is, you know, this is not an assumption, you know, it's without loss of generality. If rather than having greater than or equal to, you have strictly, then that's an assumption, and that means that there is an asymmetry. So what these two quantities are the ratio of the cost to the agent and the gain to the principal of taking action A star, rather than the agent's optimal, you know, static action when fully in 4. So we assume without loss of generality that it's higher in state omega 1 than in state omega 0. So what that means is that when the inequality is strict, incentivize, as in the example, incentivizing the agent to take A star is easier when the state is omega 0, and at the same token, knowing that the state is omega 1 is more valuable to the agent, and so as a result, the principal will gain by trying to push belief P down. Remember, P is the probability of omega 1. So we're going to be making this assumption. Okay. Now we need to define a set of beliefs. Beliefs outside this set are what I called extreme beliefs in the previous line. So these are the set of beliefs at which the agent would accept to play the favorite action for the principal if he was promised full information disclosure in the next period. So by doing A star now, the agent will get U A star P. In the next period, is going to get capital MP. So this, on the left-hand side, you got the payoff the principal gets if he does A star now and gets fully informed in the future. On the right-hand side, you do the payoff if right now the agent does what's optimal given the current belief. So beliefs in this set are important, are the belief at which the agents accept to play A star now in exchange for full information in the future. So question, is this set non-empty? Answer, if this set is empty, the paper ends here. Because the maximum you could reward the agent to undertake agent now is to tell him, I'll tell you the truth tomorrow. If that never works, you can never incentivize the agent. Notice that that's not going to imply that if the belief happens to be outside that set, you cannot incentivize the agent. You could still incentivize the agents by driving beliefs into that set. Okay, so this set from the convexity of M is an interval. Right, so this is in the interval of beliefs that I'll call it interval of beliefs that incentivize play of A star. And here is a picture. Okay, what's in this picture? So we have probabilities on the horizontal interval. We have sort of values on the vertical axis. So if the probability that the state is omega-1 is 1, well, then lowercase m1 and uppercase m1 are the same thing. So in general, capital M is is a straight line, so it's the dash M line, while lowercase m depends on what action is optimal at each stage, and so as we said, is piecewise linear and convex. Now, in this picture, I have taken the payoff of the agent to the action A star to be strictly dominated. It's below the function M. So doing the statically optimal thing is always strictly better than doing what the agent wants you to do. This is done here for expositional purposes. Later on, I'll tell you that the analysis, doesn't change from a technical point of view. Some interpretation changes. The blue line is what defines the set, underlying Q1, overlying Q1, right? So this is the payoff of the agent if doing A star now and being fully informed in the future. It's a line, so it crosses here. IQ will lower by 1, and it crosses sort of there. IQ upper by 1. Okay, so that's the interval, and and Q underline 1, so the lower level is basically also the interesting reference belief. It's sort of the principle, because of the argument that I've made of trying to drive beliefs down, is the principle would sort of like to push beliefs there. Okay. So there is also a critical continuation payoff that we need to define, and it's called WP. And this is a continuation payoff that makes the agent indifferent between playing action A star and receiving it in the future. So you could imagine that this is useful because the principle would say, do A star now, I'll give you bold WP later. So that's the solution to this. Okay. So the optimal policy, so I'm not doing that great with time, but so the optimal policy basically can be defined by the splitting the relevant area of beliefs and promised utility in four regions. There is the red regions, there is the cyan region, the gray region, and the purple region. As you can see, the splitting is by joining the payoff of Q1 and M of Q1 to 0 M0 to 1 M1, and Q star is something I'm not going to talk about. Q star will be equal to Q1 if it wasn't the case that sometimes by setting Q star equal to Q uppercase 1, the problem becomes non-concave, so we have to concavify the things to make sure that the value function of the principal is concave. And so Q star could be different from Q over line 1. I'm not going to say anything more about this because there is no time. So there are these 4 regions. And so what's the optimal policy in the four regions? Okay, so the gray region. So the gray region, basically in the gray region, what you need to do, so here you need to basically, if you look at this equation defines as splitting, but it's a splitting that splits both belief and expected utility. So what that is saying is that with some probability, 1 minus lambda, the splitting is going to be such that your beliefs are 1, and we give you and your payoff is going to be m of 1. And with some other different beliefs, with some other probability lambda, your belief will be phi, and you will be making a payoff, which is the static payoff, m of phi. So the fact that you have to split beliefs and promise utility together, it sort of imposes some constraints. So you can think about what is phi. You can think of phi as the unique intersection between the line that connects the current point and 1m1 and the graph of MP. Okay, so basically, what's the optimal policy in the gray region? The policy repeatedly incentivizes the agent to play a star with the promise of future information disclosure, splits the belief into phi and 1, and reveal, so belief 1 means you're revealing the state with the probability given by 1 minus lambda and lambda. And so if the belief realization is phi, the policy recommends action A's and promises so that the minimum possible continuation payoff that you could promise to induce a star to be done. If the belief is a 1, then the policy recommends do the optimal action, given that you now know that the state is omega 1. The policy does not leave any rent to the agent in this case. And you can think about this in this region. If this happens to be your current belief and promise utility, this is the split you do. So split. This measures sort of the split of beliefs between 1 and phi. Of course, the promise utility in the future is going to be higher than this, and so you're going to be moving somewhere in this region here. Notice that at the very beginning, at time 0, beliefs and promise utility are going to have to be on MP, but as you move along, they'll move inside the region, inside regions. So they could be in the middle here. All right. So that's region, the gray region. And how much time do I have? Okay. So the red region. So in the red region, which one is the red region? The red region is the region here. So here your initial beliefs are such that if you wouldn't want to undertake action A star, even if you were promised full information disclosure in the future. So here the principal has to give some information now. Okay. And so at the very beginning. So how do you do that? When you split the beliefs P between 0, that is to say, reveal that the state is omega 0, and underlying Q1, which is basically the lowest belief that allow you next time to say, do A star one more time, and then I'll tell you what the true state is. Now, because the fact of the fact, so the policy leaves rents to the agent. That's the answer to part of the question. And so the intuition for why it does, if you happens to be here, let's say for example, you are at the very beginning and you are on MP, you cannot find a straight line that goes from 0 M0 to Q1 M1. You have to to do so, you also have to increase, to split between full revelation that the state is omega 0 and the underlying Q1. You got to give some rent to the agent. So that is the policy in the red region, and the probability on which we do the split, so that can easily compute it. Now the purple region is similar to the red region. Here is also, if Q star was equal to Q1, this again would be a region where you can't incentivize the agent by promising full information disclosure in the future. You got to give some information now. And so that's what happens in the purple region. Again, the purple region, but now, the beliefs is very high. So the way you split it, you have to reveal that the state is omega 1 with some probability, or move to belief Q star with some other probability. And again, the promise continuation, if Q star is the realized belief, is bold W Q star. So policy recommends either to do the optimal action for the agents in state 1 A1, or to do what the principal wants. Like the red region and the purple region, the agent gets some rents. Finally, the cyan region is a region that is this region. So it's a region that never happens at the beginning, because at the beginning, you are on, beliefs and MS and utility are on M. So, but this is something that happens at the end. Basically, what happens in here, if the path of revelation leads to the cyan region, then what happens? What happens? You are here, and you cannot just provide information about one's, fully reveal one state with positive probability. The splitting constraint forces you to reveal with some probability that the state is 0, omega 0, with some probability that the state is omega 1, and with the remaining probability, you go to the lowest belief underlying Q1, and if that happens, you get the agent to do your favorite action one more time before revealing the truth. So this region can happen at the end. All right, so that's the optimal policy in the cyan region, split between the beliefs between 0, 1, and Q1, with what kind of probabilities? Well, the probability to satisfy this constraint, which basically are, promise utility constraint, belief, Bayesian plausibility constraint, and a probability I've got to adapt to 1, right? So that's how you get the lambdas, and that's what the optimal policy is in the cyan region. So a three-way splitting. So what happens if A star is not strictly dominated? If A star is not, I'm just going to go over a few minutes. If A star is not strictly dominated, there is going to be a subregion for which A star is a static best reply. So the policy that we are constructing remains optimal. It just happens that the way we are defining it may happen that the agent never learns to say. It could happen that beliefs are absorbed to the point where the splitting process reaches a set where A star is optimal, and if A star is optimal, then the agent is going to do A star forever. So that could happen if A star is not strictly dominated, but the construction that I've done works for that case too, since at that point the splitting is going to be sort of trivial, and you're going to stay, and you're always going to stay where you are. Okay, so let me then end up. So this is the last slide, this is the conclusion, and it's going to show you sort of what is the evolution of beliefs and promise utility in the optimal policy in the example. So at the starting point, the belief is 1/3. So 1/3 is the probability that the state is omega-1. And so what is the payoff that the agent would make if he undertook the statically optimal action? Well, if belief is 1/3, the agent is actually sort of indifferent. Whatever he chooses, his expected payoff is 2/3. So what does the principal tell the agent at t equal to 1? It tells the agent, take action A star. I'll promise you, I'm not going to tell you anything right now. Do A star, and I promise you the next period, your utility is going to go from 2/3 to 5/6. Then in the next period, there's going to be splitting. With some probability, I'm going to tell you that the true state is omega-1. With the remaining probability, I'm going to sort of move your belief to 3/11. So I'll move your belief below from 3/9 to 3/11. I give you the promised utility that is needed to satisfy the constraint. It turns out to be 21/22. And then what? Then I do the same thing. I keep being, in here, I'm region, gray region. So I either tell you that the true state is omega-1, or I'll move you the belief a little farther down, which is, 7/39. And then at that point, what do I do? Oh, at that point, I've gotten in the cyan region. So I'll tell you what. I'm gonna either tell you that the state is omega-1, or tell you that the state is omega-0, or move you to the belief to 1/6, which is precisely the lowest belief that could induce you to take action A star now in exchange for full information in the future. And what do I do in the future? I'll tell you everything that there is to know. So that's the optimal policy in the example, and it's the end of my slides. Thank you very much.
So any questions for Claudio?
Yeah, I have a question. So is anything interesting happens when actions are binary? So that, like, it seems that the
Yes.
Okay. So can you tell what's happening when actions are binary?
So yes, okay. So yeah, that's the line.